Thanks for having me. And yeah, this is going to be about my favorite exoplanet at this time, which is the ultrahot Jupiter WASP-121b. So yeah, we published a paper about this a couple of months ago. Here's a list of also of my co-authors, of which I think one, Joanna Bastow, is also in this room, in the Zoom room. So yeah, let's get it started. So this is an ultrahot Jupiter, WASP-121b. And we consider it an ultra-hot Jupiter because it is in extremely close proximity to its host star. So WASP-121b is a low-density planet. It's 80% larger than Jupiter, but only has 20% more of its mass. So it's a very inflated gas giant exoplanet. And it orbits its host star, which is an F-type star, in extremely close proximity. So its semi-major axis is less than 2 times the star's diameter, which makes this planet extremely hot with an equilibrium temperature of more than 2000 Kelvin, which is the threshold at which we consider hot Jupiters to become ultra-hot Jupiters, because at these really extremely high temperatures, the physical and chemical state of the atmosphere fundamentally changes, mostly due to the dissociation of molecules into atoms, and then also the ionization of these atoms, which fundamentally changes the dynamics of the atmospheres. However, at these high temperatures, we also have unique opportunities to study these planets because all of the constituents in the atmosphere are expected to be vaporized. So there's no, only for some species we expect a rainout from the atmosphere. Most species in the atmosphere are expected to be vaporized and therefore be in their observable form in transmission spectroscopy. And therefore, you have access to almost its full chemical inventory, and therefore can aim to understand its formation in much more detail than for many more other targets for which many chemical elements cannot be observed and constrained in their abundances. And on top of that, the really high temperatures make it a standout target for both emission and transmission spectroscopy, and therefore we can understand the climate of these exoplanets in exquisite detail because there's just deliver such high signal-to-noise observations. So for these ultra-hot Jupiters, one of the early questions in studying their atmosphere was if some of them have stratospheres on their day side. So this is an early work published by Tom Michael Evans, which is the day side emission spectrum of the planets of the planet observed with the Hubble Space Telescope. And for this planet, the question about if it has an atmosphere, a stratosphere, was answered with yes. So we see emission features coming from the day side, which show that there's a temperature inversion on the day side, giving us these emission features. And the creation of these day side thermal inversions isn't trivial. Not all planets at these temperatures show stratospheres on their day sides. And what we need for these day side thermal inversions is the existence of short wavelength absorbers. So the only way to create these stratospheres is to heat up the atmosphere from above. And for that, we need direct absorption of starlight in their atmospheres. So the question of what molecule or atom, like what constituent of the atmosphere creates this thermal inversion, has been a debate for quite a while. And one important study for that was the transmission spectrum of WASP-121 observed in the NIRSpec published by Josh Lothringer, which for WASP-121b here in blue shows this really strong rise towards shorter wavelength, which is commonly referred to as the NIR-UV bump. However, with the wavelength coverage of Hubble, the identity of the absorber creating this bump and absorbing short wavelength radiation in the near UV couldn't be uniquely identified. So there's two different scenarios which could explain this near UV rise. Either it's silicon monoxide in its gaseous form, or a combination of magnesium-1 and iron-2 creating this bump, or possibly also a combination of all three of these absorbers. So the only way to break this degeneracy is to extend the wavelength coverage into the near infrared. And to do that, the planet was observed with JWST. So the observation I partially analyzed was a JWST NIRSpec phase curve. And the phase curve, so there was a long stare at the planet-star system until the planet completed a full orbit around its host star. And during that, we have the notable events, which is firstly the eclipse, where the planet disappears behind the star, one at the beginning and one at the star at the end, and then the transit, so the planet transiting in front of its host star in the very middle. And the important part, the reason why the observation was carried out like this with the eclipse in the beginning at the end is that you can trace how the star's emission changes during the full orbit of a planet, and therefore then you can measure the emission spectrum of the planet throughout the entire orbit. So this is an extremely rich data set. So this contains a whole plethora of information. However, what I'm going to be focusing on, which is the part that I was in charge of analyzing, is the transit observation, which comes for free as part of this observation. So the first question we asked was if the analysis of the transmission spectrum can be done independently from the emission analysis. And therefore, we had two different analyses of the data. One was fitting the entire phase curve and the transit as part of it. And the other one, which is the one that I led, was pretending that we had only observed the transit. So basically what I did is I cut out the data, roughly the data that's shown here as this box around the transit, and then fit the transit, not considering any other and the rest of the data. And here's what the result of that was. So in blue, that is the transit standalone analysis, which is just analyzing the cutout around the transit. And in red, you see the transmission spectrum derived from the full analysis of the phase curve. And the first thing that you can immediately see is that for the full phase curve transmission spectrum, the error bars are a lot smaller by about 70% than for the transit cutout. And the reason for that is that the phase curve, so the way the emission from the planet changes around the transit, that is correlated with the transit depth. So if you look closely around the transit, the total measured flux around the transit is not a constant or linear around the transit. It has this curvature, and this curvature, to fit the light curves properly, we also have to fit for. However, if the emission around the transit were more or less curved, then the flux mid-transit would change, and therefore the difference between the transit and the baseline changes as well. And therefore, when we don't discard all data outside of this cutout, then we lose these constraints on the planetary emission we otherwise get when we analyze the full phase curve. And therefore, the precision of the phase curve analysis spectrum is a lot higher. Another thing that is more subtle to see on the upper plots, I'm also providing the residuals between the two transmission spectra, is that there's a systematic offset between the phase curve analysis spectrum and the transit standalone analysis. And that one is driven by the fact that WASP-121b, as a really hot planet, emits a lot of flux from its night side, which we cannot discern from the star's emission if we only analyze the transit by itself. And therefore, since the emission from the star is being mistaken for undercoated stellar radiation during the transit, that makes the planet appear smaller if we do not differentiate that emission from the planet from the star's emission. And therefore, the phase curve analysis transmission spectrum is systematically larger than the one from the transit cutout. And we see, since the planet to stellar flux ratio generally increases with wavelength, we see that this creates this linear offset between the phase curve transmission spectrum and the transit cutout transmission spectrum. And therefore, if we want to analyze the transmission spectrum with atmospheric models, then this can change the results of our retrievals, and we consider the transit standard analysis less reliable because it will be biased to this change in transit depth as a function of wavefront, which is not coming from absorption in the planet's atmosphere. So for the rest of the talk, I'm going to be focusing on the phase curve analysis transmission spectrum because we have good reasons to believe that that is the more precise and the less biased transmission spectrum we can measure from this data set. So here's the transmission spectrum which we observed, and maximum the results of a retrieval carried out with the Nemesis atmospheric modeling framework. And you can see a couple of clear spectral features in this spectrum. So this downwards slope, which is very often seen in NIRSpec transmission spectra of exoplanets, is created by water absorption. Then there's a massive CO feature on the longest wavelengths, which creates this abrupt rise in transit depths at wavelengths longer than 4.3 microns. But in between those, there's also another molecule which conveniently absorbs starlight between 4 and 4.3 microns, and that is silicon monoxide, SiO. So this detection is generally in line with silicon monoxide's hypothesized impact on WASP-121b's near UV transmission spectrum. So this is a really informative data set, and the planet itself, well, the first thing we did is that we compared this transmission spectrum as we see it from this analysis to three-dimensional models. So in the literature, there was a general circulation model, which was published on this planet specifically. So you could just go to the literature and pull out the transmission spectra of this planet to compare to our observations very conveniently. And here's what that told us. So in blue, you can see the model transmission spectrum derived from the fully three-dimensional nature of the atmosphere, if no dissociation of neither hydrogen nor water or any other molecule in the atmosphere is considered. And if that is the case, then the water feature we observe is much shallower than what the model predicts. And also the CO rise is barely visible. So the model has to be missing something. So what they also in this paper showed is how the model transmission spectrum changes if they include, like on a post-processing stage of the atmosphere, include dissociation of molecules at different steps. So if they first only consider the dissociation of water in the atmosphere, then we see this model, the orange model spectrum. So the water absorption feature is flattened out a lot compared to the dissociation-free atmosphere. So water dissociation improves the fit to the observations greatly. However, the CO feature is still far from what we observe it. So when the authors, when they additionally post-process H2 dissociation on top of the atmosphere, then the CO feature rises all the way to the levels at which we observe them. And generally, including both H2 and H2 dissociation, the fit to the observations is actually pretty impressive. So three-dimensional effects such as thermal dissociation seem to play a vital role in this target. And the reason why the CO feature is affected by H2 dissociation, but the water feature is not, so you can see that between the models including H2 dissociation and not including H2 dissociation, there's barely any difference in the water feature. And this dichotomy in the impact of H2 dissociation on the observed transmission spectrum indicates that these two molecules, water and CO, are absorbing starlight in very different parts of the atmosphere. And to visualize that, here is an equatorial cross-section of WASP-121b's atmosphere with the star on the left, and then the observer in this picture would be sitting on the right. And the starlight we observe filters through both the very extended day side and the much more compressed, because of cooler temperatures and recombination of molecules, night side. Then CO behaves very differently than water in the atmosphere, because CO is naturally the most stable molecule in the atmosphere, and therefore the CO gas is present all over this atmosphere. So the signal from CO we observe will be completely dominated by absorption of starlight on the day side, which is because the day side is so much more inflated because of thermal expansion and dissociation of molecules. Water, on the other hand, dissociates itself, and therefore the day side, which is so extended, will be more depleted in water than the night side, and thus the water absorption feature will be dominated by the thermal conditions on the night side. And therefore, and that is precisely the reason why we see this dichotomy between the sensitivities of CO and water absorption in the atmosphere, because H2 dissociation only occurs on the day side, and therefore it only affects the absorption of CO, which also absorbs in the day side. So clearly, to derive the chemical abundances of the atmosphere, we need an atmospheric model that is more complex than a simple one-dimensional assumption. And therefore, Jordan Bastow, with the Nemesis retrieval framework, implemented a dual atmosphere setup in which the atmosphere, so the chemistry and temperature in the atmosphere, gets split into day side and night side hemispheres, and then the rate through the light is integrated across the line of sight. So on the hot day side, she parameterized the temperature profile with a 3-parameter GO profile, then allows H2O and H2 to dissociate, which we expect to play an important role. Also, there's absorption from ionized hydrogen and a constant CO abundance. On the cool night side, on the other hand, she prescribes a non-inverted PT profile, which we believe will be a good assumption, given that from phase curve observations, we know that there's not a thermal inversion on that hemisphere. And their chemistry is constant with height, which is a fine assumption because we don't expect a lot of thermal dissociation there, and also a constant CO2 abundance. Some of the chemistry we expect to not vary greatly between the two hemispheres, most importantly the CO the CO abundance, but also SiOH and SiO abundances we fix between both hemispheres, as well as cloud opacities and cloud top pressures. So here are the retrieval results we found from both the Nemesis dual atmosphere setup as well as other atmospheric retrieval frameworks which operate on the classical one-dimensional assumption. So firstly, from the PT profiles, the Nemesis model, the day and night side to PT profiles, you can see in magenta and in purple, successfully find a thermal inversion, as we also have seen it in phase curve observations on the planet's day side, and a regular temperature profile, so temperatures decreasing as a function of height on the night side. Then, though we see in the chemistry that the results between the different retrieval frameworks vary. So for the Nemesis framework, the model does favor a lower H2O abundance on the day side than on the night side, which is exciting because this is in agreement with water dissociation happening on the day side and not happening on the night side. And this means since the undissociated water abundance on the night side is the one that we expect to be closer to the bulk chemistry of the planet, this means that the one-dimensional frameworks, which agree in terms of their H2 abundances in the atmosphere, however, since they do not account for this dichotomy on the planet's in the planet's atmosphere, they might underestimate the bulk of water abundance of the planet, which is more closely represented by the nightside abundance we find. However, a couple of discrepancies between the models also are concerning the carbon monoxide abundance. And we believe that the reason for these dichotomies is that the impact of H2 dissociation is not represented in all of these models. And since the CO absorption feature is not only set by the CO abundance, but also H2 dissociation, this will change the CO abundances the retrieval frameworks find. So when I change the bottom two panels and show the H2 abundance in the atmosphere, you can see that like all the different models find different degrees of H2 dissociation, which could be driving the differences in CO abundances. So for example, for example, the Nemesis framework, which finds fairly little H2 dissociation, does finds a very high CO abundance, whereas, for example, the equilibrium chemistry models, which find a lot of H2 dissociation, find lower CO abundances. So this could be in line with a degeneracy between H2 dissociation and CO abundance. All right, I think I'm about to run out of time, so let me quickly sum up what we find from WASP-121b's transmission spectrum observed with NIRSpec G395H. So firstly, exciting news is that we see, for the first time, gaseous silicon monoxide in an exoplanet's atmosphere. However, the challenges in analyzing these observations is that this transmission spectrum is a composite of the day side and night side opacities, which are simultaneously probed in transit. So the next step forward we took is that we implemented an atmospheric retrieval framework, which accounts for hemispheric inhomogeneities, which for these kinds of data sets will be an important step forwards trying to constrain the bulk chemical abundances of the molecules in the atmosphere. Thank you.
Thanks very much, Cyril. If anyone has a question, just click raise your hand, and then you can unmute and ask a question. Yes, Anna.
Hi, sir. Very nice talk, very cool results. I have two questions, but let's start with the first. When you see the dissociation creates a strong feature in the models at 4.8 and a much less strong line profile around 4 microns. Is there, yes, like here, do you think that is still within the noise, or is there any other explanation that might be more chemistry to consider?
Oh, so you mean the data that's not fit around here?
Yes, and a 4.8 peak that seems to be one of the strong features in the dissociation.
Yes, one thing I forgot to mention is that around here, so between 4 and 4.3 is where SiO absorbs. However, the three-dimensional model did not include any SiO opacities. So that bump is missing in this model because that molecule is just not considered. So for this one really high point around here, I don't exactly know why that's doesn't seem to fit that well with the observations. So here we definitely expect carbon monoxide to be the dominant absorber. And I'm not sure like if there's a line list accuracy about why this feature is so strong in the model but not in the observations. I'm not sure. But the overall level of the data between 4.4 and the end of the longest wavelengths of the observations is fit fairly well, which
I'm pleased with.
Thanks. That's nice.
You
Any
had a second question?
I have a second question. So you're making basically a two-sided easy comparison, but I was wondering, does the phase curve support this kind of the shape of a split hemisphere model, or can you actually see a decrease in scale height at the limbs or in the dawn region of the planet already when you look through the phase curve and look for the shape of the emitting regions?
Yeah, great point. We haven't looked in much detail at the phases in the phase curve that are not exactly like not the closest approximations of the day side and night side hemispheres. So yeah, that's definitely an interesting point for the future to see if the emission spectrum coming from each limb individually, and to see how exactly that varies, how abruptly temperature and chemistry seems to change. So yeah, that's a good point, but we haven't looked into that yet.
Thank you. Very cool data.
Thanks.
Does anyone have any other questions they'd like to ask? I've got a question. So with the atmospheric retrieval technique where you're doing 2D atmospheric retrievals, what sort of like temperature range of planets would you say this is possible to like apply to, and like what sort of level of signal to noise do you think you need to actually be able to use this technique?
Yeah, so I'd say firstly the physical parameter space in which this approach is the most adequate for would mainly be the hottest planets, because the radiative timescales become really short at these high temperatures, and therefore the day to night sides asymmetry is extreme. So for these, it's the most imperative to move to these sorts of models. Whereas for cooler targets where the radiative timescales are longer and therefore winds can redistribute heat more efficiently and the temperature gradients across the terminator get smoothed out, are lower on the priority list. So the ultra-hot Jupiters are the first obvious go-to targets for this retrieval setup. Whereas in colder targets, we've seen with JWST a lot that one also important factor is to discern how the radiation, like how absorption in morning and evening limbs differs, which is something which we haven't considered in our retrievals for this work yet, because we didn't see a detection of limb asymmetries. So for the colder targets, the different spectra between morning and evening limbs might be more important than this. So for this, I'd say the first obvious important targets are the ultrahots.
Thank you very much. Can we thank Cyril again, please?